So today we will be covering second order system impulse response, second order system frequency response. So first of all we will start with impulse response of second order system. Now as we did in the first order system, we considered that there is input for a infinitesimally short time, and after that the system responds or system works on unloaded conditions. There is no imposed input on the system, and then we analyze the response of the system. Now here in this case also we will start with the governing equation for second order system, that is d square by omega n square plus 2 zeta d by omega n plus 1 qo is equal to k qi. The governing equation is same for all the cases, only boundary condition will change, and boundary condition is qo is equal to 0 and dqo by dt is equal to ka omega n square, because a term has come due to area of that rectangle which we have taken into account while doing the first order analysis. So the area, and that is representing the energy input, that is coming into the picture, and this is at t is equal to just after t is equal to 0 plus, and this is in this case with these boundary conditions. If we analyze the system for the cases, let us say overdamped, when zeta is equal to greater than 1, when there is an overdamped system, then the output or the response of the system is going to be qo by ka omega n, and I will write on the board it is going to be, when the system is overdamped, qo by ka omega n is going to be equal to 2 times under root zeta square minus 1 plus, we will take the roots, e raised to power minus zeta plus zeta square minus 1 omega n t minus e raised to power minus zeta square minus 1 omega n t. So this is the response when the system is overdamped. Now in this type of system, if we look at the transfer function, the transfer function is the block representation of this system is, or the second order system is this is qi, and this is your transfer function d square by omega n square plus 2 zeta d by omega n plus 1, and then we get qo. So this is how the input output relationship in such type of systems is depicted. Now if we break this block diagram, then we will get, this is omega n square, right, and omega n, before omega n square and after omega n square there is a differentiation. If you remember, if we differentiate the step input, it becomes impulse, right, and then this qo is, this is qo, then qo is again differentiated, now we will connect this here minus plus and first differentiation. 2 zeta by omega n, sorry, omega n, it is connected here after first differentiation. And then before that, there is again, this is plus and this is minus, and this signal is coming here, and then it is K, and then it is Qi. Now we have broken this system in the parts. Okay. After first differentiation, we have taken this omega n by omega 2. Then after second differentiation of the signal, then omega n square has been differentiated 2 times. This one has been differentiated 1 times. And this is how we can represent the signal in block diagrams. Now the input is, as in the case of impulse input. Input we always define by A by T. Input is defined by A by T, or there is a pulse. Pulse can have any shape. Shape of the pulse does not matter. So there is a pulse. So input is a pulse at t is equal to 0 plus. So input is a pulse of area A, right, at t is equal to 0 plus. Now after this transfer function, the pulse becomes K. This is area, this is A is area, right, and this continues here and this continues here as well, and then after this omega n square, this block, this pulse become Ka omega n square. Just we have broken transfer function in the number of parts. Now this is going to get differentiated here. When the pulse is differentiated, now this is the case when the pulse is differentiated, and when the pulse is differentiated, it is going to be like this, and this is Ka omega n square. And from here we will get the Qo out, and this after differentiation it is going to be multiplied by this, right, and after that it is further differentiated, then it becomes a vertical line. Okay, and this is how the entire block diagram is completed. Right. Now if the system is critically damped instead of over damped, system is critically damped. When the system is critically damped, then we can write the equation as Qo divided by Ka omega n is equal to omega n t e to power minus omega n t. This is the case when damping ratio is 1. And similarly, with the available boundary conditions, we can derive the equation for underdamped system also. For underdamped system, this equation is going to get modified as √1 minus zeta square e raised to power minus zeta omega n t sine under √1 minus zeta square omega n t. So depending upon the value of damping coefficient, we can use any of this. We will use the particular equation which is applicable for the value of damping coefficient. Now after this, we will start with the frequency response of second order system, right? Now in frequency response of second order system, frequency response. For first order system, if you remember, we have taken the amplitude ratio, let us say m is equal to k by under root 1 plus lambda omega whole square. This was for the first order system. Now here, the governing equation is qo by qi I omega is equal to k by I omega by omega n whole square plus 2 zeta omega by omega n plus 1. This is the transfer function for frequency input or sinusoidal input or frequency input. Or the sinusoidal transfer function, this shall be used to finding the solution for, we need only two information in the frequency response when there is a sinusoidal input. What is the amplitude ratio and what is the phase lag? Here the phase lag was, or phase angle was tan inverse omega lambda minus omega lambda, or phase lag was tan inverse omega lambda. There is never phase lag in the response, because the system cannot respond before the input is given to the system. So there is always, ideal case is phase lag is 0. But the replication of input to the system is more important than the phase lag. Suppose we reduce the phase lag and the signal is distorted and we are not giving the actual output what is given to the input. The system is not giving actual output which is being given to the input. Then the purpose of measurement is lost, right? Because this phase lag can be compensated, but distortion in the signal cannot be compensated. So the instrument, a well-designed instrument, replicate, it can be mirror image of the input to the instrument, the output of the instrument, or measurement by the instrument can be mirror image of the input, but it can have certain amount of phase lag and that can be taken care of by certain compensations, right? Now here the amplitude ratio in second order system, the amplitude ratio is qo by k divided by qi I omega is equal to 1 by under root 1 minus omega by omega n whole square of this plus 2 zeta omega n, 2 zeta omega by omega n whole square. Or, and this output may be lagging by certain angle phi, and phi is here, phi is, I will write here, the phi is tan inverse 2 zeta omega by omega n minus omega n by omega. So now we have both the expression for both the values. This is amplitude ratio and this is phase angle, phase lag, or we can, if we replace omega by n for the sake of convenience, if we replace by omega n by r, then this is going to be one by under root 1 minus r square whole square plus 2 zeta r whole square. Just for the sake of remembering the things. And here also we can write 2 zeta, this is omega by omega n, omega r square minus 1, and right, you multiply numerator and denominator by r, then you will be getting 2 zeta r by r square. So this is easy to remember, right? Otherwise both the expressions are same. Now response of the system. These are the equations, and always the damping ratio plays a major role in deciding the ratio of output and input amplitude and deciding the phase lag in the measurement. Now let us see the characteristic curves for output and input. Qo by K upon Qi, right? And this side we have taken omega by omega n. Okay, and we have started from 0, 1, 2, 3, we can go up to 5, 4, 5, omega by omega n. So on abscissa we have taken omega by omega n, and ordinate we have taken the output ratios. Now this is 1, this is important, this is 1, and vertical line we can have markation as this is also 1, 2, 3, 4 and so on. But this also, there is a characteristic point, so here also we will draw one horizontal line. Now zeta is equal to 2. Now zeta is equal to 2 output and input ratio, because it is a damped case, because damping is there. So the variation is with omega by omega n is going to be like this. This is zeta is equal to 2. Next is critically damp, zeta is equal to 1. Now critical damp will also go something like this, but it will soon, it will come here, right? Then it will come under damped system, 0.6, 0.8, 0.4. So up to 0.6, let us, this is 0.8. This is 0.6 will not cross. It will just be just a little over here, and then it will come down. It will come down somewhere here. Now I am not able to draw the exact figure. Approximately they are going to be like this. They will converge at one point. They will converge at one point. This is for zeta is equal to 0.6, and this is for zeta is equal to 0.8. Now damping ratio will further reduce. If the damping ratio is further reduced, then we get, there is a hump, 0.4. We further reduce the damping ratio, then there is a 0.2, then 0.1. Like this, when there is no damping, this will go to the infinity. That is the case of resonance. Resonance will take place if the damping is 0. And at the same time, phase angle. Now we will draw another figure for, now here we can see that between 0.6 to 0.8, in fact actually between 0.6 to 0.7, we get this almost flat somewhere here. more frequencies are available. That is why I stated earlier also, while choosing an measuring instrument, we should look for the damping ratio between 0.6 to 0.7. We can go up to 0.8 also, but not more than 0.8. So best range is 0.6 to 0.7, where overshoot will not be there, significant overshoot will not be there, and we get more frequencies in this range. Either the curve is almost flat in this range, or for the range of frequency for which the curve is flat is higher for this zeta, when the zeta is lying between these two. Now we will draw the characteristics curve for phase lag as well for frequency response. Now for phase angle, because phase angle is always negative, as I said that the response cannot lead the input, so it is always negative, it is 0, and it will go up to minus 180 degree. But in phase angle also minus 90 is important. We will draw one line at minus 90 degree, and one line we will draw at 1 here, and then it can be 1, 2 and 3, 4 and so on. Right? Now first curve we will draw for zeta is equal to 2. Zeta is equal to 2. The zeta is equal to 2 curve will come like this. This is zeta is equal to 2. Right? Now we will move towards reducing the damping ratio. Right? So zeta is equal to 1. Zeta is equal to 1 will something like this. Slope will start increasing. Now this is going to be for zeta is equal to 1. This is zeta is equal to 1. Then we will go for underdamped system. When the underdamped system is there, then it will start taking this type of curvature. Right? So both sides it will be having the, if we reduce the damping ratio, the both sides it will be, the nature of the curve will be sharper. There will be sharp terms in the curve. This is zeta is equal to, or zeta is equal to 0.1. Right? So here in this characteristic curves, by referring this characteristic curve, we can get certain idea about the normal response or the general response of second order measuring system for frequency input. Now if we take some critical points, if we take certain critical points for measuring instrument, then suppose omega by omega n is equal to 0. When omega by omega n is equal to 0, m is going to be 1 and phi is going to be 0. Because m we have calculated, m is equal to 1 by 1 minus under root 1 minus r square whole square plus 2 zeta r whole square, right? And when omega by omega n is equal to 0, then this expression is going to be 1. So we will get m is equal to 1 here, phi is equal to 0 because phi is equal to tan inverse 2 zeta r by r square minus 1. So this is going to be 0. Now omega by omega n is equal to 1. When omega by omega n is equal to 1, m is going to be 1 by 2 zeta. If this no damping is there, then it is going to be infinity. That is perfect resonance because, sorry, this is omega by omega n. Because it means the imposed frequency is equal to the natural frequency. When imposed frequency is equal to natural frequency of the system, m is going to be 1 by 2 zeta if there is no damping. Or damping is, say, zeta is 0.01. In that case, n will have very exorbitantly high value. Then phi is equal to, in this case, is going to be minus 90. This is lag. I mean 90 degree or phi is going to be minus 90 means it will be lagging by 90 degree. Now if omega by omega n is equal to infinity, imposed frequency is very high, 1 lakh cycles per second. Natural frequency is 1000 cycles per second and imposed frequency is some millions cycles per second or million radians per second. This is imposed frequency divided by natural frequency. So imposed frequency is much higher than the natural frequency, right? So in that case it is going to be infinite. When omega by omega n is infinite, so definitely m is going to be 0. When imposed frequency, physically if you try to understand this phenomena, if I impose the physical frequency on this table and the frequency is say 1 billion cycles per second, the table has got its own inertia. So we cannot feel any movement in the table, right? Same is the case here. When omega by omega n is infinite, the ratio is going to be 0 and the phi is going to be minus 180 degree. These are the values at certain salient points, and there is a case when we call resonant frequency. Resonance frequency is the frequency when dm by d omega by omega n is equal to 0. That is known as frequency of resonance, right? So resonant frequency here is resonant frequency WR is equal to omega n under root 1 minus 2 zeta square. So once we have the damping ratio, we can find the resonant frequency of the system. There is one more phenomena that is known as dead time element. Dead time now in dead time element, the system, it is a system which is defined as the system in which the output is exactly as the same input. Output is exactly same as the input, but after certain time lag, right? For example, there is a pneumatic system. Suppose there is a tube filled with air. There is a pneumatic system, and tube is pressurized here. The air pressure is exerted here, and the length of the tube, let us say, is 350 or 360 meters. So when the pressure pulse will move, suppose it moves with the velocity of sound, right? So after 1 second, you will be hearing exactly the same sound. There is a time lag, but we are getting the exactly same input. As I said earlier, the nature of the signal should not be distorted. So nature of the signal is not distorted, but we are getting a signal after a pause. So this is known as dead time element. This is all for today. From the next lecture, we will start with the higher order systems. Thank you.